Hello, this is section 3.3, Graphical Solutions. Warm-up example. Graph the solution to the following system of inequalities. So the first thing I'm going to do is find the boundary lines. So x plus 5y equals 50. Subtract x. 5y equals negative x plus 50. And then divide by 5. When we get y equals negative 1/5 x plus 10. So that has a y-intercept of 10, and then a slope of down 1 over 5. So there's our first boundary line, and it should be solid because of the less than or equal to. Now do the next line, 2x plus y equals 28. Subtract 2x, y is equal to negative 2x plus 28. Fortunately, 28 is not on here, but if I find the x-intercept, you get 14, because negative 2 times 14 plus 28 is 0. So my x-intercept is 14, and then I have a slope of negative 2, so up to the left 1. And there's our second boundary line. And then we should have a horizontal line and a vertical line at 0 and 0 respectively. But remember, that just means we're in the first quadrant, which my graph is already in the first quadrant. So next is to pick a test point. I would pick the point 1, 1. Well, 1 plus 5 times 1, is that less than or equal to 50? Check. 2 times 1 plus 1, is that less than or equal to 28? Check. Is 1 greater than or equal to 0? Check. And is 1 greater than or equal to 0? Check. So we get this shaded region here. Now, this is from the previous section of notes. What we are going to do now is extend it a little further for what is called linear programming problems. So example 1. Now let's say we have a function f equals 1.5x plus 0.5y, where x and y are subject to the constraints or the inequalities in the warm-up example, and we want to maximize f. Now what this means is we have this function f, which because it has 3 variables in it, it is going to be a 3-dimensional object. And to help us visualize that, I do have something up on Desmos. So let me switch over there. So right now, what you're seeing on the screen, this is what we just graphed. That's the same shape, just a little zoomed in. Notice I'm going from 0 to 14 on the x-axis, 0 to 10 on the y-axis, and we have the intersection point of 10, 8. So that all works well. But now I'm going to graph the 3D function, and when I first click it, it looks like it's just over top of it. That's because when you look at it from above, because of the constraints, it will look the same. But as I tilt it, you'll see that it's like coming up out of the floor at this angle. And you can see that it is above. So it itself is still only 2 dimensions because it's called a plane, but it's being graphed in the 3-dimensional cubed. And it does connect down to the shaded region. That shaded region, and we'll write this in the notes later, is called the feasible region. So you can see how it's occurring right above it. So when I say I want to maximize this function, which is in red, that means I want to find the highest point of it. And if I turn it just right, we'll see the highest point occurs at this corner, which is right over this point. So what point was that again? Let me do this. That was 14, 0, that point. Before we go back to the written notes, though, I want you to realize in this class, we're only going to deal with these types of objects. They're called planes. And because they're completely flat, I hope you realize that if we're trying to maximize or even minimize it, because notice we have a minimum value down here at 0, it has to occur at one of the corners because it's a flat piece of plane. If there were curves in it, that's not necessary because it could curve up higher than one of the corners. But if it's completely flat, it has to be maximized at one of the corners. Now, why is that important? Because normally we can't graph in 3D by hand. And if we're working with something, don't have a graphing calculator on us, we're going to want to do this by hand. But from this, the rationale is to do it by hand is you start, there we go. You start with the shaded region and you find the corners of the shaded region. And then we plug those into our red function, and whichever one gives us the highest value, that is our maximum. Or whichever one gives us the lowest value, that is our minimum. So let's get back to the written notes. Okay, so like I said, we need to find the corners first. Now the corners do have a special name. They are called vertices. And usually I start in the bottom left. So here the bottom left vertice is 0, 0. And then I go clockwise. That's 0, 10. This was 10, 8. And I do want to make a comment. Notice how this was the y-intercept. I'm writing it too low. This one is the x-intercept, which is 14, 0. But in general, if it does not graph nicely, you have to find the coordinates of this point, and that's where you're going to use elimination, substitution, or even matrices sometime. So just keep in mind, we still have to use ideas and concepts from chapter 2. Well, now I have my vertices. I'm going to plug them into the function. 1.5 times 0 plus 0.5 times 0 is 0. 1.5 times 0 plus 0.5 times 10 is 5. 1.5 times 10 plus 0.5 times 8 is 19. And then 1.5 times 14 plus 0.5 times 0 is 21. So we were correct. There was a maximum at the point 14, 0. And then how we write our answer is f, subject to these constraints, has a maximum of 21 located at 14, 0. Now the reason why we have to say subject to these constraints, and I'm going to go back to Desmos now to show this. Let's say I take these constraints off of f. Then I get this plane, which is just cut off at our viewing window. But if I make my viewing window bigger, let me do this. Let's just go to 100. It just keeps going off forever and ever. So look at our constraints down here. It just kept going forever. So if we don't have constraints, these actually will never have a maximum because it goes on forever. And then sometimes, even with constraints, if our constraints, let me hide this, are not bounded, so we were lucky here the constraints are bounded here. It doesn't go off to infinity, but sometimes you will get constraints that go off to infinity. For example, let's say if we didn't have these two, that these constraints are going off to negative infinity. Let me change that again. So this would, without the 0, 0 constraints, these go off to negative infinity, which would mean we don't have a minimum in this case. So the only time you're guaranteed a maximum or minimum is if our feasible region is bounded. If it's not bounded, you can have one or the other or neither. Okay, now back to the notes. Now, like I said, we're going to go through the definition. Constraints are the inequalities or conditions we are subject to. The objective function. This is the function we are trying to optimize. Now, optimize is just the catch-all word to say minimize or maximize. The feasible region is the region bounded slash shaded by the constraints. The corners of the feasible region are called vertices. So, solutions of LP problem. So, LP is the acronym for linear programming. When the feasible region for a linear programming problem is closed and bounded, the objective function has a maximum value and a minimum value. When the feasible region is not closed or bounded, the objective function may have a maximum only, a minimum only, or no solution. If a linear programming problem has a solution, then the optimal, maximum or minimum, value of an objective function occurs at a corner of the feasible region determined by the constraints. If the objective function has its optimal value at two corners, then it also has that optimal value at any point on the boundary line connecting these two corners. So remember, our objective functions in this class are going to be planes only, so that means no curves. So if two of the corners have the same value and we have to have a flat plane between those 2 points, that means that entire edge connecting the corners has to be the same height as well. So we'll get the same value. So in those cases, you'll get many solutions, not just one or two. And I think that's a good place to stop for the first part of this video.